Okay, good morning everyone. Welcome to the second day of the Directive-based GPU Programming workshop here. Today we will go over a few things that are what some people would call more advanced OpenACC. So some things that are a little bit more complicated than just using just launching kernels or executing parallel regions or the data movement itself. The first thing in this series of more advanced topics that we will go over is asynchronous execution. Now, what do we mean with that? Basically, if you look into the OpenACC standard or into any material, it's anything that has to do with async clauses. And I'll show you what that is in a moment here. Basically, everything that you've seen so far was using a very simple model for the execution. All the kernel launches and all the data movements that we've done were blocking. That is, we initiated a kernel launch from the CPU, and the CPU thread will wait until the kernel completes on the GPU, and then we continue execution. So we're really switching back and forth between one and the other. And the same is true for the data movement. At the beginning of a data region, we would trigger a data transfer, but the CPU would wait until that transfer is complete and then continue with the execution of the program. So far, that's all that we've done, okay? There are some other possibilities in the OpenACC programming model, however. What happens under the hood in the runtime system with these operations is they all get put into a default queue from which they're executed. And in this default queue, everything is executed in the order in which you put it in. So the first operation you put in is the first one that gets executed, then the second one, and so on. Now, you could easily think of some algorithms or programming motifs where you have packages of work that are independent of each other. And I'm not talking about the iterations in a parallel loop now, but really different pieces of work where you don't really care for the order in which they're executed or if they are getting done at the same time or something like that. So the question is, how can we map that to the functionality in OpenACC? Okay, that's what asynchronous execution is about. Very simple example. Imagine we have two arrays and we just want to sum them up. Okay, so we have an array A and array B. We want to calculate the sum of the two, and we need to put some values in here into A. We need to have some values in B, and then we create the sum. So far, when you would write this as a small example program with the directives that you have so far, this is what would happen, right? You would have one kernel that writes some values into A, and then you launch a second kernel that writes some value into B, and then you have a third kernel that actually computes the sum of the two. And there might be some additional data transfers between those, okay? But if you look at it from the point of view of which operations are independent of each other, well, the two initializations are completely independent, right? So ideally, we could have something like this. These two can be executed at the same time, or we don't really care if they are, they could overlap. B could be initialized before A, doesn't matter for us. The only real constraint that we have, the only real dependency on the data that we have is that both of these need to be initialized at the point where we create the sum. But it doesn't matter in which order we initialize these, okay? And there are many algorithms and many program structures that have at least pieces like this, where you can express more parallelism in this way by exploiting that you don't need to execute everything strictly in the order in which it is located in your source file, let's say. Okay? The way this is mapped in OpenACC are the so-called async queues. That's a short term. In full, if you look into the OpenACC standard, these things are referred to as asynchronous activity queues. What these are is basically a set of queues, and every kernel and every data movement that you write can be put in any of those queues. Within each single queue, the same holds what I said before for the default queue, that is, all the operations are executed strictly in order. So if you put an operation into a given queue and then you enqueue a second operation, you're guaranteed that the first one will happen and will complete before the second one starts. However, all these queues are independent of each other. So they can execute at the same time, they can overlap part of their operations. The only real governing point here is in how far there are resources free on the GPU. You know, if some queue has a data transfer that could be executed and the resources are free, there's some bandwidth free, that can happen while some other queue does a computation or does some other data transfer as well. Or if you have a set of very small kernels, none of them actually fills the GPU, but they sit in different queues, then they could all be executed on different SMs and basically happen simultaneously. Okay? The way this is done is through the so-called async and wait clauses and directives, and I'll show you the syntax for those in a few moments. For those of you who have programmed CUDA and think that this sounds awfully familiar with CUDA streams, yes, that's what it is. In CUDA terminology, these asynchronous activity queues in OpenACC are CUDA streams. If you don't know what a CUDA stream is, it doesn't matter. You'll still get how this works. Any questions up to this point regarding these queues and the basic idea of having multiple queues overlap in time? Yeah.
If you forgot to leverage this parallelism for some obvious piece of code, is the compiler able to do that for you, or never?
No. Basically what the compiler does is it puts all these operations into a default queue. And you really need to express if you want something else to happen. For some very simple cases, I agree with you that probably from a compiler perspective, it would be possible to determine some independent pieces of work. But for anything like a more complex compute kernel and data transfers and so on, it very quickly becomes very complicated. And without human input, that's a hard problem to solve. So basically, you as the programmer have to put these things in if you want them. If you don't, if you're not using these clauses here, then you get a program like all the examples that you've seen yesterday. A default queue will be used, and all the operations are blocking on the CPU thread that launches them. Okay? Any other questions so far? No? Okay. Then let's see how these work. The async clause takes an argument in, which is an integer. The same goes for wait. And this integer number is an argument that denotes the specific queue that you're putting something into, or that you're waiting for. And I'll show you the syntax in a moment here. Async is a clause that you add to the things that you already know, the directives you already know, to basically tell the compiler that this given operation should go into a given queue. Wait, on the other hand, is basically a barrier, a synchronization point. You can imagine that if you launch a lot of work into several different queues, then from a programmer's perspective, you will reach some point where you need to make sure, well, from here on, I need to have the results back on the host and continue execution from there. And that's what wait is used to create such barriers. Using these async and wait clauses can significantly improve the performance of your program. We've said yesterday that for every kernel launch, there is some amount of overhead just for launching the kernel. It really depends on your program, but there are some algorithms that have a very large number, and I'm speaking thousands, of very small kernels. So there's not a lot of work in each of them, but there are really very many of them. And this launch overhead then can become something that you can feel in terms of the overall performance. If you can use these queues, then basically you enqueue all the operations, and you can hide that overhead quite well. Now, let's take a look at a simple example what these things looks like. We have two loops here. There's some work inside, which I haven't actually specified. We have ACC parallel loop, like before. That's your normal kernel launch. And then async gets added here as an additional clause to that. And in this most simple example here, I've just used the same queue for everything here. So we launch this kernel into Q1. The CPU immediately continues execution after putting it into the queue. So then this kernel here is added to the same queue. The CPU continues execution right away, and then we reach this barrier here, and we're saying at this point we wait for everything in Q1 to complete. Okay? So that is almost the same functionality that you had yesterday without using these, with the one change that between these two there's not an additional barrier. But in principle, this would execute almost like the examples that you've worked on yesterday. Okay? Of course, that's not where we get the most benefit, but just so that you get an idea for the syntax of these clauses. If we go to something more useful or more instructive, let's assume here we have some outer data region that moves our data to the GPU. Or that allocates the data on the GPU, and the structures are all there. Then we have a loop here over a given number of planes, and we copy the data for a given plane P to the device. That's this update directive that Vasily mentioned yesterday. Then we launch a kernel on it that does some work on the plane P, and after that we update the data on the host again. So we copy it to the GPU, we do some work on it, we copy it back to the CPU, and then there's this outer loop here which does not get executed in parallel on the GPU. It's basically a driver which just steps through all these independent planes. Okay? The way this is written right now, everything executes in order, right? The plane P plus 1 will only start copying and then getting the kernel launched for it once the plane P is already finished, okay? If we look at that in a more graphical representation, the upper panel here is what we would have with this current loop. So there's the plane P, there's a host-to-device transfer, that's the update device directive, okay? Then we have the kernel launch for the plane P, and afterwards we have a device-to-host transfer, that's the update host directive, where we push the result back to the CPU. Once the plane P is done, plane P plus 1 starts executing, and we repeat the same pattern until that outer driver loop completes, okay? In principle, what we could do is overlap these things, because we said these planes are independent, right? So we could have something where on the outer driver loop, we put these operations into a queue, but then as plane p+1 is completely independent of these three operations, we could start pushing that into a queue as well, right? And we could get overlap here. For example, the kernel launch or the kernel execution on plane P could overlap with copying the data in for p+1 already. And we could overlap that, and basically the kernel launch would, on p+1, or the kernel execution on p+1, could overlap with copying the data back to the host for plane P. And you see here where you basically overlap these things, and overall you of course get a much faster execution time. Yeah? I've shown this here a little bit like the profiles in NBVP that Vasily showed you yesterday. In a real example, for a real application, of course, these panels or these blocks here are not all equal size. Your transfers could be much larger than the kernels. They could take much more time than the kernels if you're copying a lot of data but don't do a lot of work on them. And these things could also shift. It doesn't mean that there has to be a synchronization here. For example, if the outer driver loop is done putting all these things into the queue, and it goes to the iteration p+1 and starts to put that plane into the next queue, then this transfer here could also start overlapping with this one, if resources permit that. So it really depends on the data transfers and the size of your kernels, okay? But as a basic concept, that is what it would look like. Now, the question is, how do we write that? How would we need to change that example that I showed you to make that work? Well, we need to put these clauses here, async. So the update device directive gets an async clause, the kernel launch gets one, and the update host gets one. Okay? And then after all this is completed, at the end of that outer driver loop, we need to put in some synchronization, because presumably we would like to work with those results that we've just computed. Okay? Now, the argument P here on the async clauses, we could write something ourselves, right? We could have a sort of my list of Q indices that you can start with 42 and then increment in steps of 5 if that is what you choose. But very often, there is already something in your program that denotes the independent pieces of work. In our case here, it's the iterations of this outer loop, of this endplanes loop. We know that every iteration P is independent of the other iterations, so we might as well just use that and use it to denote our queues here. For the runtime system, it doesn't matter whether you start at 0 or whether you start at 10, and if you go in some steps that are not a stride of 1, or if you increment it by 1. It doesn't matter at all. It's really just something that denotes a specific queue.
So basically, in previous slide, you said that you want to start the execution of kernel 0 and data copy of 1, right? But when you write something like this, async P, yes, then would it start? Wouldn't it start it simultaneously? Execution of data transfer for 0 and 1.
If the resources on the GPU are free,
okay,
then they could overlap.
Okay.
Yes, all we do there is we put the operations into different queues, and the hardware on the GPU basically looks for what work is eligible to run, what has been queued, what resources are free, and if there are enough free resources, it will try to overlap things as much as possible.
So just a question. So if you have a small problem, then if you do blocking of the algorithm, then it would be faster with this async. If it's like if you make a block of a loop.
Could be, yeah.
Okay.
It really depends on how much data you have and how big the kernels are in terms of runtime.
Is there any limit in the number of queues that you can use?
Not really, because they are wrapped around. They are mapped like CUDA streams. So the runtime system will keep them separate, but from a programmer's perspective, you don't need to make sure that you stay under a given limit or something like that.
But you...
Oh. Sorry.
But you can keep in mind that effectively you won't have as many as you want.
Yeah, but on the other hand, for example, for this thing here, it wouldn't make sense to put an outer loop here that basically tiles the n-planes loop to whatever the physical limit of the queues on a given hardware architecture is. It just doesn't matter.
Yeah, right? Just you won't get some, say you have a very small data transfers, for instance, you won't get the same acceleration as if you had effectively all independent queues.
Possible, yeah.
Yeah,
possible.
Just to keep that in mind.
Is the clause update device and update host necessary here, mandatory, or could be avoided?
It could be avoided in the sense that to get the correct result, we wouldn't need it, right? We could copy the entire array in at the beginning, and we could copy the entire array out at the end. Sorry, the question was if the update directives here are really necessary for the program, okay? They aren't to get the correct result. We could have something where up here we do a data copy in of plain of the whole array, and then here we just have work packages, and at the end we copy it out. For performance reasons, we want those update directives though, because otherwise we can't overlap these transfers here with the execution of kernels, right? We would have one data movement at the beginning, and it couldn't overlap with any of the kernels. Then the kernels themselves could overlap, but after that, we would take away the transfer back to the CPU again and have that run in one block, right? If we write it with the update directives, we get this overlap of the different pieces, and that actually is something that's faster.
So just to clarify, Pragma ACC data, you're not copying the planes, or are you also there?
No, this would be something like a ACC data create planes.
Okay,
yeah.
thanks.
Or whatever else might be needed in that inner kernel there. Any other questions regarding that example? I think you get the idea, right? Wherever you have something that you as the programmer know, you have pieces of work that are independent, this is a way to express it to the runtime system and then let it schedule on whatever resources are available, okay? So that's almost all that is to be said about these async clauses. There are a few things that can be a little bit confusing if you try to gather it from the standard or from some other examples, because wait is not only a directive. There's not just a Pragma ACC wait, but wait can also be a clause on these, and you can have combinations like this. So I just wanted to show you on a few examples what this actually means. This here would be a parallel region, a kernel, that gets put into queue number 5. That's what the async clause does. But at the same time, we put in a barrier for queues number 4 and 3. So we create a synchronization between Q5 and Q4 and 3, and we make sure that this kernel here will only start executing in queue number 5, where we've put it, once all the work in 4 and 3 so far has been done. You could write this with a different wait directive, but you can pull it all together and that way have a synchronization there between those. Okay? Looks a little bit confusing. Huh? So it's really just a combination. If you would not have the wait clause back here, this is exactly the thing that you've seen in the previous example. We're putting the work into queue number 5. That's all that the async clause does. Now, if we add the wait clause here, it means at the same time, for the beginning of this kernel, we put in a barrier and say, but only start executing this in queue number 5 if all the work in 4 and 3 up to this point has completed. So it allows you to express dependencies on different work packages.
Sometimes it could be useful, maybe, is it possible to have, instead of real integer hardly written in the queue number, could you have an integer variable or a label?
Sure. Okay. Like the P in the previous example, right? It's, you can use variables there, or you can use parameters, whatever you like. Just, it needs to evaluate to an integer number. Yeah. Is this clear now, what this does? There are a lot of situations where you don't really need these things, but if you really have something that is fairly complex in terms of the control flow of the different pieces of the algorithm, there are situations where something like this can become useful. Okay? Another question back here.
So, okay, we said Q5 should wait the work in Q4 and 3 to finish, but does it also start the work in Q6, or does it also wait for 4 and 3 to finish, so in order to 5 finish and then switch to 6?
Q6 at that point...
Or is it independent?
Q6 at that point would be completely independent. All we're doing here is saying 4 and 3 need to be completed before this, this piece of work in queue number 5 starts. All the other queues, 6, 1, 2, whatever, run completely independently. If there are resources free, their work will get scheduled and will get executed. Okay?
So is there some data dependency here? And we will see it later. How does it work?
You mean with what is in the loop body here?
Yeah.
No, I mean, I just put a simple stencil operation there for some averaging. The idea here is that whatever you have in the other queues would not necessarily, like it could have, for this kind of loop, maybe what has been put into the other queues could be some computation for the array Y, let's say, something like that. Yeah, but it's really just arbitrary here. It's just an example. Any other questions? Okay, then the other example that I'll show you here, just so that the meaning of this syntax is clear. Before, we had pragma-ACC wait without an argument. That means you wait until everything that has been enqueued up to that point completes. If you want to wait on just a specific queue, then you can have the wait directive and specify which queue you want to wait on, or a set of queues as a comma-separated list, like in the previous example. Okay? We can also have this kind of directive here. It's a wait directive that has its own async clause. And that pretty much does the same thing that we had before here, where we put that directly on a kernel. It's kind of the same thing, but as its own separate directive. We're saying we're creating a barrier. We need to wait for everything in queue number 3 to complete. And we put this operation into queue number 5. So after this point, whatever whatever gets enqueued into 5 will have to wait for the completion of everything in 3 up to that point. It's basically the same construct as this, but here we've added it as clauses on an actual kernel launch, on a parallel region, and you can also write the same as a separate directive here. And these combinations sometimes can get a little bit confusing if you look at examples, or if you look at all the combinations that are possible in the OpenACC specification. That's why I just wanted to show you a few sort of common examples and make sure that you understand what they mean. So in these cases, the actual thing that happens is a wait directive, and we can specify which queue we want to wait on, specifically just some queue number instead of all of them, and we can also put that wait operation into a given async queue. Yeah? Or we add that to our actual kernel. You can express it either way. Any further questions? No? Everything understood? You can write the most complicated pipelines now with, with async clauses. Okay, we'll get to that in the hands-on session. But this is basically everything that I have to say about the asynchronous queues. It's really an addition that you don't need to use. It's not required for correctness. But if you have pieces in your algorithm or in your programs where you as the programmer know you can create some overlap here, then it is a very useful thing to just utilize the resources on the GPU more. Vasily mentioned that yesterday on the Pascal GPUs that we have here on Dained. We have some 56 SMs, streaming multiprocessors. The next generation hardware Volta has 80, so you can run some almost 5,200 CUDA threads simultaneously at the same time. And these resources are getting harder and harder to keep them busy, right? You have a lot of functionality on those chips to execute things in parallel. And if you don't use things like this here, then it can be a little bit tricky to actually utilize all of it. If in the previous example, if the amount of work that you would execute on a given plane is fairly small, and your planes are a few hundred by a few hundred points or something like that, then it would be very hard to utilize even a Pascal or possibly even an older GPU very well. Whereas if you have a few thousand or a few 10,000 of these small planes with small work packages, and you write it as in the previous example, you're launching a lot of work. Yeah? You're launching a lot of work basically as fast as you can from the CPU side, and you just let the GPU chunk through it, resources permitting. So it can really be something where it allows you to keep a GPU more busy. And as GPUs, the newer generations so far have always been more powerful and had more resources. So it becomes a little bit of a challenge to actually keep those resources busy. And this is one way how you can do that. Okay. Vasily, do you want to take over?